So we would like to compute this double integral, and since the domain is so much easier to represent in polar coordinates, we would like to do this in polar coordinates. Let's recall that if we have an integral that is originally given as usual in Cartesian coordinates, then to rewrite it in polar coordinates, we really need to do three things. So first of all, we need to rethink of the domain as in terms of polar coordinates. So we need to describe the domain in terms of polar coordinates. That's the first thing. The second thing is that we need to rewrite the integrand in terms of r and theta. So x will become r cosine theta, and y will become r sine theta. So that's the second thing to do, take care of the integrand. And finally, we need to multiply by the Jacobian, which accounts for the computation of the areas of the rectangles over which the usual Riemann sums are considered. So these are the three steps. Okay, so first step, second step, and third step. Let's take a look at this case, and let's take the first step. Okay, so let's represent the lower half of the disk of radius 2. Here's what it looks like in terms of polar coordinates. So this will be all the r's and thetas, so that r is between 0 and 2, and theta runs from pi to pi. Okay, so that means that we can start writing the integral. So it will be from 0 to 2 dr, and from 0 to, I'm sorry, not 0, we said pi. So pi to 2 pi d theta. And our function is y. So y is the same thing as r sine theta. And we also have to multiply by r, the Jacobian. So we carried out our three steps. Okay, so let's take a look at them again. The first step is to come up with the endpoint of integration. The second step is to come up with the correct integrand. And the third step is to multiply by the Jacobian. Now, we can continue with our computation. And let's integrate first with respect to r. So you have an r squared. Its antiderivative is r cubed over 3 sine theta. And you want to go from 0 to 2. Sometimes what we do is we write r equals 0 to r equals 2, especially when we have more than one variables, to emphasize the fact that this is taken with respect to r. So this will give us an 8/3, and the 8/3 can go in front. And we will have the integral from pi to 2 pi of sine theta d theta. What is the antiderivative of sine theta? Negative cosine theta. So we will have negative cosine theta from pi to 2 pi. And what do we get here? So we have negative cosine of 2 pi. That's the same thing as negative cosine of 0. That's negative 1. So we will have negative 1 minus, and what is cosine of pi? So I'm sorry, what is negative cosine of pi? And negative cosine of pi is negative 1, which is again 1. So this will be negative 16 over 3. And sometimes there might be a little bit of a surprise here. Oh, we found a negative number, but the integrand was not negative. No, actually, the integrand was negative. If you look at the problem, you have a function which is equal to y, right? And y is in what territory? It's in negative y territory. So in fact, it should not be a surprise that we found a negative number. And that tells us what? That pretty much the graph of this function is below the xy plane. And since the integral represents signed volume, the corresponding region whose volume we're computing is below the xy plane, and that's why it counts as negative. And so it makes perfect sense that we found a negative number. And that's all we needed to do. Thanks for watching.